got ourselves a very, very nice FRQ to deal with here. This is an acid-base FRQ, the type. Consider this a way of showing really what you know, and to prove to the graders that you've got down AP chemistry. Show off. It's a good idea to look over the entire FRQ to get sort of an overview so you can get the right mindset to solve this sort of thing. Now, you can see immediately from the top that we have ourselves a ammonia. That's a base, a weak base. We know that. Dissolved in water to make ammonium ions and hydroxide ions. Okay, it's a weak base ionizing to make a mildly alkaline solution. Let's read it over quickly. In an aqueous solution, ammonia reacts as represented above. Yeah, we've read the equation. Now they give the specifics. In 0.31 molar ammonia, the hydroxide ion concentration is, they're going to tell us how alkaline this is, how effective the ammonia is in producing a basic solution. Now they want us to write the equilibrium constant expression. That's easy. They want to find the pH of this solution. That shouldn't be too tough. Determine the value of the Kb for the ammonia. That might be a challenge. Determine the percent ionization. Okay, we've heard of that before. If the solution is diluted with pure water, how will the pH and the percent ionization change? Good. Then finally, F, the last one. In an experiment, we've got a titration, 10 mLs of that ammonia solution, the 0.31 molar stuff, is put in a flask and titrated to the equivalence point. It's neutralized using a strong acid, 0.186 molar. Find the volume of the acid to reach the equivalence point and determine the pH of the solution in the flask after 8.3 mLs of HCl has been added. Okay, that's it. We've got it. This is just a pure acid-base reaction. And right now, I've highlighted the important values, the 0.31 molar ammonia and the hydroxide ion concentration. Now, let's see. What's the first thing to do? Write the equilibrium constant expression. Okay, they want to know if you can write an equilibrium constant expression and can put the products over the reactants. That's not tough. We know that. We've done that many, many times. That'll be worth 1 point, a nice, fast, and easy one. So just put that K down. That equilibrium expression constant is going to be equal to the products. And we know the products here for A. I'd always put down the letter where I'm going to answer things. And that's going to be the ammonium ion, the products, that little plus charge, in brackets to indicate molar concentration. You've got to use the brackets, times the hydroxide, that's our products, and then divided by our reactants, but you're not going to include water because it's a liquid. This is nice, simple arrangement. So that's it. Products over reactants. We've eliminated the liquid because its concentrations change. Check that one off. Next, determine the pH. Well, we know we're going to have to do a lot of things. So let's put together a nice chart for this. There is so much to do that it's really worth getting everything organized in here. So let's write the equation out. Simple enough. We've got the time to do it. It's worth the investment. And start off with the initial. Now, we're starting off with 0.31 molar ammonia put into water. So our ammonium product is going to be 0, and our hydroxide is effectively 0. There's going to be a change. Okay. Now, there's that other piece of data that they give us, which is critical. They tell us at the end that our hydroxide concentration is 0.0115 molar. That's the equilibrium amount. As soon as you end up getting two values in a nice chart, you can figure out the third. And once you've got the change, follow the stoichiometry, and you've got the entire chart. At equilibrium, you're going to have the subtraction of the amount of ammonia that ionized. I'd get a calculator out to do this just to make sure that you don't mess up a subtraction. You know, on a test, you're sometimes under pressure, and even a simple subtraction can create a slight slope up can mess things up. So get the calculator out, double check. It's worth the time. So there we go. I've got my calculator, did the subtraction, and there we go. 0.29, and I'm going to run it off to 8. You could run it up if you wanted. It doesn't make any difference. Now we know exactly what's happening in equilibrium. So let's see. For B, they wanted the pH. Well, they gave us the hydroxide ion. And we know that the pH is going to be equal to 14 minus the pOH, and the pOH is simple enough to get. Show your work. Take the hydroxide ion concentration that you've got there on your equilibrium chart. Take the negative log of it. So I'll have Alexa figure this one out for me. The Chem Edition. Alexa, what is the base 10 log of 0.0115?
The answer to your calculation is minus 1.939302.
Of course. There we go. We've got our pH of 12.06. That makes sense. It's a mildly basic solution, and you would expect that it'd have a pH of greater than 7. Always check your answers to make sure they make sense for you, that you didn't mess up. Don't be blinded, or don't go mechanically. Make sure they make sense. Now for C, they want to know the equilibrium constant, which we've got the expression for. Let's just plug the numbers in and do the math again. The number makes sense. It's a weak base. Now, I would, since you've got this in your calculator already, I would immediately take the negative log of that to get to pKb. You've got the number in your calculator. You want to use it to help you a bit, and then get the pKa. That's always valuable. And just, again, use that calculator efficiently. You don't have to retype the numbers in. Just use the last answer, subtract from 14, and you've got your pKa beautifully. And that's going to come in handy eventually. It's worth the extra few seconds. All right. We've found out the ionization constant and quickly calculated the pKb and pKa. Even though they weren't asked for, we figured that they'll come in handy later on. Percent ionization. Okay, that's a very specific equation. You have to remember that it is equal to the amount of ions you've got, the hydroxide ions, and they gave us that, divided by, this is where you've got to be careful, the initial amount of base that was there. Now, don't go by the equilibrium amount, because you want to know how much of the stuff that we put in actually ionized. So we're going to put in the 0.115 molar for the hydroxide and put in the 0.310 molar for the percent ionization times 100. Get ourselves a nice small number. It's a weak base, I should say. So turns out to be 3.71%. next part is something that you really should end up remembering. It's been asked a lot. On dilution, there's a greater chance for the molecular substance to find some water molecules that donate or accept protons. So whenever a weak acid is diluted, it ends up ionizing more and more. A greater percentage of it will. So always the percent ionization increases. But because it's diluted, even though more of it ionizes, it's diluted so much more that you really don't get a greater pH. The pH is going to decrease, but of course it's going to end up decreasing to 7. You can't get any more diluted than 7 in water. So there you go. Answered part E. And now for the last one, which is a titration. That's really worthwhile. Labeling base, base, acid, acid, because they're easy to mix up. When you've got a titration and you're going to reach the equivalence point, you can use the concentration equation. It's a 1-to-1 stoichiometry. So here we go. We're just going to get concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. Check up there so you don't get the numbers mixed up. It's such an easy calculation, and the only error you're going to make is if you put the numbers in the wrong locations. So the acid that we're using is our hydrochloric acid, a strong acid. We don't know its volume to neutralize this base, but we know the concentration of the base is at 0.130 molar, and we have 10 mLs of it. Our calculator comes in handy here, and voila, our answer is going to be more than 10 mLs for the acid, because the acid isn't as concentrated as the base. So you're going to need more acid than base. And indeed, the answer comes out to be 16.7 mLs of your acid. Yeah, the acid's that much less concentrated, so you're going to need that much more of it to completely react with the base. Now, finally, they want to know the pH, not at the equivalence point, but at the 8.3 ml mark. Now, that might be a real tough calculation, but there's a shortcut around it. Typically, the last question on a FRQ has a sneaky, easy method of solution. Notice 8.3 mLs is half of 16.7. It's the half titration point, and half titration points are easy. At a half titration point, the concentration of the unreacted base is equal to the concentration of the conjugate acid that was produced. And when that ends up happening, the pH equals the pKa. That's it. That's all you have to write. At the half titration point, pH is equal to pKa. We check up our little calculation we did at the ice chart and write down that answer as a very easy 10.65. Now double check, does that make sense? Yeah, this is a weak base. We have totally titrated it. So it's going to be slightly alkaline. And that's it. You've got yourself an entire FRQ that you really have an 18-minute time limit for. And doing it nicely and slowly in an organized manner, you can get it done with plenty of time left over. That's it. A tough FRQ on acids and bases. And I tossed in a little pH curve just as an extra description of what happened, where we start off at a alkaline solution, dips down, we get the buffered section, then run down to the equivalence point, and That's it. Half titration point there. Equivalence point there.